Welcome back, everybody. I hope you had a great start of the week. We're actually getting close to the weekend now. I want to give you a quick overview of what we plan to do today. And then we're going to look a little bit further ahead as well on what is going to come and the kind of elements we need to fill in order to get a better understanding of the different simulations which we're going to run. So the topic today is to deal with important sampling. We are going to take a kind of top-down approach first. So we're going to look at practical aspects. We're going to look at how we can implement this and computational issues. And then we are going to, a little bit later, to dive into the topic which is not perhaps not the easiest one. It's about the Fokker-Planck and Longitude equations. The thing which we did last week was to derive the Metropolis algorithm. We also derived what we called the Metropolis Hastings algorithm, which is normally used in what we normally call important sampling. So the standard Metropolis algorithm, the way we would typically implement that is that we would have a set of random walkers. And these random walkers are jumping around in configuration space or space, like in our case, just plain coordinate space. And they are jumping around according to a fixed jumping length, which we call the step length. And this is a parameter which we often tune so that we accept roughly 50% of the suggested moves. That's a kind of rule of thumb. And there is nothing deeper than that we just accept a certain amount of suggested moves. Now, this is not the most efficient way. You can actually do the sampling. And the idea then is to change this by guiding the random walkers according to some kind of probability. So the way we are going to define this probability is actually in terms of the gradient of the wave function. So I'm going to give you first a small motivation for what is going to come. Then we're going to go back to the slides and we are going to look at how we can implement this and what are the kind of technicalities we need to deal with when we are writing the code. And then when we've gone through all these kind of small details, we are going to take a closer look at what is this Fokker-Planck equation and why do we use the Fokker-Planck equation. And from the Fokker-Planck equation, which is a very important equation if you're doing studying topics like fluid mechanics, you're dealing with transport theory, you may encounter the Fokker-Planck equation. And the way you can view it is that you take the standard diffusion equation, and from the standard diffusion equation, you add a force or an external field which governs the motion of the particle. So in addition to kinetic energy, which you would have in a diffusion equation, you have an external applied force. Now, in our case, this kind of machinery is then used to guide the random walker in its jumping in coordinate space. And in our case, it happens that this kind of external force is given by the gradient of the wave function or the trial function which we have. And then there is an important equation which is called the Langevin equation, which in principle is you solving Newton's equations, but with added noise. And this is the equation which we end up with when we're going to suggest a move. Now, the equations which we end up with, they also do have parameters. And one of the parameters is going to be a so-called time step when we solve this Langevin equation. So even though we claim that we are doing important sampling and we have a better way to guide the random walker, there are going to be parameters. And if you think back to the brute force jumping, the parameter there was the step size which we would fix. And then we would adjust it so that we accepted roughly 50% of the suggested moves. Now we're going to look at a more, how to say, a better way of letting the random walkers jump. but they're going to be guided by this Langevin equation. And this Langevin equation is in principle the solution of Newton's equation of motion with an added noise. And it has a time step when you solve it. If you think of Euler's method for solving a differential equation like Newton's equation of motion. And this time step is the new parameter. So our results will depend on that time step which we choose. So there's no way to escape new parameters. But hopefully, this is a slightly more fundamental approach. And with important sampling, you don't need to use this kind of rule of thumb where you accept roughly 50% of the moves. Now, one thing I wanted to do before we jump into the top-down technicalities of what we need to implement and how we can implement it is to remind you about what we did last week, and then to try to motivate why we need this Fokker-Planck equation and why we cannot get away with just the plain diffusion equation. So what I'm going to do now is to switch back to the whiteboard after these few motivation words for the what is going to come here. So let me find my pen here. So what we did last week was to derive what we called the Metropolis Hastings algorithm. And this is based on the theory of Markov chains. And the Metropolis Hastings algorithm is the algorithm which now tells us whether we will accept or reject a suggested move. And it gives a detailed balance between you jumping to higher probabilities and jumping to lower probabilities. So remember from last week that if we only jump to higher probabilities, after some few jumping around in our coordinate space or a more abstract configuration space, we would simply be stuck in the region with the highest probability. And that means that the values you would sample in order to evaluate a multidimensional integral would be extremely biased by you being locked down in just one place. So the Metropolis Hastings algorithm was based on what we called detailed balance from a Markov chain. I quickly remind you of some of these topics from a Markov chain. And if we now go back to what we defined last time, so we have a probability of being in a specific state. And we call this Wi, and this could be in a given state at a time t. So I could be a specific state. In the most simplest case, this would correspond to a position in space, like our random walker. We then also have what we call the transition probability, which is normally not known. And we represented that by a matrix. And this matrix is what we call a stochastic matrix. So we go from a state J to a state I, and this is typically indicated with a matrix element Wij. So we have a model for the probability. In our case, this is the wave function squared as a function of the position of the different particles which we're moving, and the variational parameters, which we need to fine-tune in order to find the variational minimum. Now, the transition probability is an unknown quantity. And that represents complicated physical processes. So it can be difficult chemical reactions, and many of these quantities are very difficult to calculate. And even if you can have an analytical expression for it, these will typically be multidimensional objects. And so even if you have an analytical expression, it will be time consuming to sample from it. So the whole theory of a Markov chain is then based on us defining the likelihood of being in a new state I as a sum of all the previous states, and then we do this transition from j to I, and this is multiplied with the probability of being in a position in a state j at a time t minus 1. So it depends only on the previous time steps. So this is the basic definition of a Markov chain. And this matrix, as we expressed it now, we are looking at discrete events. It can turn into a continuous object. In principle, the number of events we have, or the number of states we have, which we can sample, is infinite. Now, what we did next here was to define a model for this transition probability. Since this is something which we don't know, then we are free to model it. And we model it in terms of a transition probability, which tells us what is the probability of making the transition. But we haven't accepted the transition yet. And this is now given in terms of what we call an acceptance probability. So keep in mind that the stochastic matrix is an unknown quantity, and we are in a way free to model it. And sometimes we have deeper insights about the way it should look like, but we would normally only have a partial insight. So this is normally called a transition probability, the probability of making the transition. So the total transition probability we have on the left includes also you accepting the move. So this is a transition probability. And this is you accepting this move. So this is normally called the acceptance. And the Metropolis Hastings algorithm, what it gives is actually the acceptance probability. So the Metropolis Hastings algorithm is then given in terms of the minimum of 1, and then the ratio between you being in the state Wi, and then you have a transition probability. So let me just rewrite this one. So this contains now the transition probability of from I to j divided by Wj of t of j going to I. Now, the assumption we made last week is that t of I is reversible. So it means that when we go from I to j, this has the same likelihood as going from j to I. So in some simpler systems, like you flipping spins, you have the same likelihood for picking a spin. If you have n such spins, you could now assign a likelihood of 1 divided by the number of spins. So that means that you picking a specific one and then flipping that spin, so that means you go to a new state, has the same likelihood as doing the reverse operation. So that's a case which normally leads to the standard Metropolis algorithm. What we want to have now is a model for this Tij. So we are going to assume now is that Ti over to j is different from T of j going to I. And that leads normally to what we call the Metropolis Hastings algorithm, where we have to evaluate or have a model for this transition probability. So let's now go back to some basic properties of the diffusion equation. So if we now look at the link with the diffusion equation, so I mentioned that you can derive the diffusion equation from a Markov chain. So the process of diffusion is intimately linked with Brownian motion and Markov processes. So let's now look at a simple way by which we now can try to find this transition probability. So let's now start with a very simple initial condition. And we have a discrete probability. So we assume now that our initial distribution, and let's call this Wi at time 0, could now be given by a delta function, delta I, and then I put a 0 here to indicate that this is time 0. So this is just a Kronecker delta. Now, when we now make a time step, suppose we make a small move here, then we would have a Wi at the time. Suppose we do this t, and we make a small step epsilon. Then this will be given by the sum over all the transition probabilities, where we also have the acceptance, multiplied with this delta function, or we can just write it more generically like this. So in this case, we have a delta function. Now, what we could do now is to move to the continuous case, and that is where we are going to make the link with the diffusion equation. So if this was a discrete case, so we have discrete events. So if we make the continuous choice, what we would have then is that this probability, this Wi of 0, goes over to a W of x. So x is now a vector which represents the position of the specific object, or if you have many objects, this could be a multidimensional probability. And this is now going simply to be given by, so this is at time t0, this is going to be given by a delta function. Okay, so if we now look at the continuous version of the Markov chain, so let's now move from a discrete version to a continuous Markov chain. Now, what happens then is that we would now be in a new position, and I call this new position for y. There is a t plus delta t. I'm just writing this in a more general way now. And this contains now an integral over all the positions in a domain which we are looking at. And there is a transition probability which will depend on the final state, the initial state, and we keep these as vectors. And there is a time step, delta t, and normally this transition probability is assumed to be time independent. And then we multiply this with a W of x of t, and this is finally multiplied with d of x here. So this is an integral over all the positions which you could be in at a time t, and then you integrate this up with a weighted probability, and that gives you the new probability. So you could think of your object, which could be a drop of milk in your cup of coffee. So it could have an initial distribution when the milk molecules are just localized to be represented by a delta function. And then gradually, as you move on with time, these milk molecules, they spread out through the whole cup of coffee. There's a kind of example which we discussed last time. That reminds me that during the break, I need to fuel up with some coffee. Now, what we could do now is to, and this is a standard trick which we do, is to rewrite this in momentum space, because then we can actually solve the diffusion equation in momentum space. But we are going to look also at the case when we have reached equilibrium. So that is the situation when we have reached the most likely state. Then the system is going to be a system which, where the particles or the object we are looking at are just going to jump in and out in equilibrium between different positions. So when equilibrium has been reached, then there is no time dependence anymore. So then our probability would simply be given by this Wi. And now we would have an integral with x over the domain of events. And our transition probability is now also assumed to be independent of time. So you can have a time dependence during the process here, but that clearly complicates everything. Now we are assuming now that the equilibrium has been reached. This is a steady state, and there is no time dependence anymore. So this will now give us a Wx of d of x. So this is the equilibrium variant of the discrete equations which we saw last week, which we use then to derive detailed balance. Now, one of the things we can do next is to find this probability Wx as a function of time. So what we do now is that we keep time. Just a reminder that this is the way it's going to look like, but we can actually solve, we can find this Wi. If we're not looking at the equilibrium situation and we want to link this with the diffusion equation, we can actually find that one by making a Fourier transform to momentum space. Normally what we call K-space, or momentum space. So if we now look at a given probability, so let's just look at x as a function of t here. If we now make a Fourier transform, we would have an integral from minus infinity to plus infinity. And Fourier transforms are actually extremely useful mathematical tools. So we would have an I over k multiplied with x. And then we would have a probability now, which is defined in momentum space as a function of time. And this is an integral over dk. I hope you have seen Fourier transforms before. That's an extremely useful tool when we are, for instance, want to solve, let's say, differential equations, or we want actually to represent a pulse as an expansion in terms of sine and cosine functions. So the useful thing now is that the delta function has a representation given by exponentials. So we can actually look, if we look at the delta function, this is going to be given by the exponential of ik of x. And integrated over k, the domain of values of k here. Now, if you do that, you can now easily see that this w tilde of k0, if we now look at the definitions, it's not so difficult to show that, is actually given by a constant, which is 1 over 2 pi here. So if I insert that one as my initial probability, you can then look at the Fourier transform diffusion equation. So I'm assuming that you have seen some of the theory for Fourier transformations. And if we now look at the diffusion equation, that means that we can integrate up the diffusion equation in the spatial degrees of freedom, and then we can rewrite it in terms of the momentum degrees of freedom. So the standard diffusion equation with only kinetic energy, we would have a Wx of t of dt, and that's given by a diffusion constant times the Laplacian of w of x of t. Now, when you make a Fourier transform, and this is one of the reasons why we like Fourier transforms or Laplace transforms, is that the differential operator just turns into a constant, which is the momentum squared. So if you look at the Fourier transform diffusion equation, then what we would have is a differential equation for the Fourier transformed probability as a function of time of dt, and that's just equal to a constant minus d of k squared, and then we have a w tilde of k of t. Now, this is something which is pretty easy to solve, right? So when we simply integrate this up, this gives us just an exponential. So what we would get then is k of t, and then we know the value at t equal to 0. So that will be given by w of k0 multiplied with the exponential here of minus d of k squared times t. So that means that when we plug in the value of this probability at time equal to 0, we have 1 over pi exponential of minus d of k squared of t. Now then, what I can do next is to plug this back again into the expression which we have up here. So if you look at the expression here, I know the probability in momentum space because I solved the diffusion equation. And the thing which I'm not giving you, and please apologize me for that, is the link between the diffusion equation and a Markov chain. So I'm just stating that you can derive the diffusion equation from a Markov chain and vice versa. But I'm not showing it to you. That would take me at least 2 lectures in order to derive these equations, these relations. So I hope you can just accept it, that you can derive the diffusion equation from a Markov chain, or you can take the diffusion equation and go to a Markov chain. So having the diffusion equation now with only kinetic energy, where you have the Laplacian of the second derivative of the distribution, means that you can transform that to momentum space, and then you can find the distribution in momentum space, assuming that you start with a delta function. And then you can go back and you can integrate up again. So we would get the distribution as a function of x of time here. And this would now simply be given by the integral from minus infinity to plus infinity. And then we would have the exponential of I times k of x. And then we would have to multiply with 1 divided by 2 pi. And then I would have a new exponential of minus d of k squared of t multiplied with dk. And when I integrate this, I get a famous distribution here, which you probably have seen many, many times before. So I'm just setting up the result. So it's a 4 pi of d times t. So time enters here. And then we have the exponential. And then I have a minus x squared divided by 4 dt. And this is nothing but a Gaussian. So if I am now making a transition probability, so if this is now going to represent my transition probability, we can actually, what we can show now is also that based on this diffusion equation, we can also show so I can solve the same type of equation as I did for the probability here. I can now replace the equation for the probability, which I plugged in here, and I can plug in the transition probability. So the probability which we have obeys the diffusion equation. And since this is a Markov chain, it means also that the transition probability has also to obey the diffusion equation. So if we just stick with the diffusion equation, what we can show then is that this probability, which we defined of Wy of x, and then performing this operation within a small time step delta t. So we go from a time t to a time t plus delta t, and we only are looking at the time differences. This is now given by, so it's actually not that difficult, just some involved differential integrals to be solved. And this is multiplied with delta t. And multiplied with the exponential. And then we have a minus of y minus x squared divided by 4 d times delta t. So this is a Gaussian, which is now given by y minus x squared divided by 4d times delta t. And the denominator in the argument of the exponential plays the same role as a variance of a Gaussian distribution. So this is just nothing but a Gaussian distribution. So when you solve the diffusion equation, the probabilities you get are actually given by Gaussians. And that's a very, very important result, because it also motivates the usage of Gaussians in many physics calculations and modeling of physical processes. If we now go back to our Metropolis Hastings algorithm, so what we were looking at in the Metropolis Hastings, so the reason why I wanted to discuss this now is that I want to relate this to the Metropolis Hastings algorithm. And in this case, we have now a model for this W, and we could say that this is now my transition probability. So what I would have is that my acceptance ratio, which I need to evaluate, which is this Wi multiplied with this Ti to j, divided by Wj of T of j going to I. And now we are going to assume that this Ti to j is proportional with this Gaussian, which we have derived. So this would be an exp, and then we're going to write it like a minus 1 y, and you could now think of y being your final state. So we put an I here, minus x, which is the initial state, and this is divided by this 4d times delta t. So the question I'm going to ask you now is, so what I could do now is the following. I could assume that my random walkers are random walkers which jump or have a transition probability given by the solution of the diffusion equation with just the kinetic energy operator. This solution has a nice analytical form, and I could actually plug this into my Metropolis Hastings algorithm. Now, if you look at this distribution which you have, what strikes you, if I plug this in here, what would I get as a result? Just take a look at the expression here, and you look at the ratio between the u going from a state I to a state j, and from a state j to a state I. If I take the ratio between these probabilities, what do I get? So feel free to unmute yourself or just write the answer in the chat. So what happens if I plug this in here and in here? So what am I going to get on the right-hand side if I use the solution to the diffusion equation without any modifications?
Wouldn't you get Wi over Wj?
Yes, exactly. So our first attempt at making something slightly more intelligent and having our random walkers to be governed by a probability which we can calculate by solving the diffusion equation seems to be failing, because we are back to where we were. So this is where the Fourier-Planck equation comes in. So we would need to modify this. So we need a modification. And what people have done in the field of Monte Carlo simulation. So this is not only done in a quantum mechanical simulation, but it's something which you would also actually do if you were to simulate other processes. So what we need now is a modification of the plane diffusion equation. And the first kind of modification which can be done and which has been used widely in transport theory and in fluid mechanics is something which we call the Fourier-Planck equation. So I'm going to point to you the derivation of the Fourier-Planck equation, but now we are going to use it. And we are going to look at the equations, and from that, we can say something about a minimal form of what this transition probability has to look like. And then with that minimal form, we can then try to go back and solve the diffusion equation. And actually, the Fokker-Planck equation is widely used by a very, very simple reason. You can actually solve it analytically. So, and that gives you an analytical expression for this transition probability. So what you will see now is that this transition probability, this Ti to j, is going to be pretty similar to what you have here, but you will have a modification. And that modification is going to be given by the gradient of the trial wave function. And that is going to link the way we jump into space with the starting point, which, and our starting point is the trial wave function. And because that defines the quantum mechanical probability distribution. Any questions so far? I just wanted to give you this kind of background because you can then see why we introduced the Fokker-Planck equation. I hope you can forgive me also for not having shown the link between the diffusion equation and the Markov chain. And I'm also assuming that this stuff with Fourier expansions is something you may have seen before. So Fourier expansions are and Fourier transforms are widely used techniques in mathematical physics, for instance. And if you're taking a course in mathematical physics, you have most likely encountered Fourier transforms. If you're dealing with imaging and signal treatments, Fourier transforms is basically your daily operation, actually. So let's go back to the slides now and try to link what we are doing now with an improved type of calculation here. So what we are going to do now is to give you this kind of overarching view on the equations which we need to program. And then when we're done with that, we're going to look at some of the computational elements and how to implement it. So in the lecture notes, you will find Jupyter notebooks, which you can run, and you can see how to implement this new transition probability. And then finally, if we get time, we're going to look at the connection between the Fokker-Planck and this Langevin equation. So, but first we are going to take a kind of overarching view. If you wish to read more about the stochastic methods and Markov chain, there is an excellent textbook by Gardner on stochastic methods in science. There's actually a link here to a previous version. There's also another text if you want to read more about Brownian motion, Markov chains, and the Fokker-Planck equation. There is a text by von Kampen, which is just called I think it's just called Markov chains. So what we are going to do now is to assume that we have a time-dependent probability, Px of t. This is our Wx of t, which I discussed in the lectures here. And if you look at the case in just one dimension, and assume now that you have a random walker, or just a particle which jumps around in space. So what you have now is the standard diffusion equation, but you have added to this one a drift term. So you can think of this drift term as a kind of force, which now forces the particle to move in a specific direction. So it could be the particle which is now moving with kinetic energy in a gravitational field. So the Fokker-Planck equation, which you will find the derivation of in the same slides here, but a little bit later, gives us now a changed diffusion equation. And this is the starting point, which we will use when we now are going to try to find or make a guess on what this transition is going to look like. So in our case, P here is going to be the transition probability. It could also be the probability for being in a position. But this is the Fokker-Planck equation. And there's another equation which is intimately linked with the Fokker-Planck equation. which is called the Langevin equation. So the Langevin equation actually follows from the Newtonian mechanics, but you could now think of an object which is moving, so this would be the velocity of an object, which is now moving according to some constant times some kind of force here, plus some random variable. So you have some fluctuations. So these are meant to mimic the rapid fluctuations you would have due to the background, to noise, or things which you cannot quantify. Then you can integrate this up. So this is a stochastic differential equation. And this is the equation which is now going to govern the way we set up new positions. So you can integrate this up. There's going to be a Gaussian variable. So we always assume Gaussian variables. So this eta is a Gaussian, and this xi is a Gaussian. And then you can show formally, so I'm just giving you the answer. So there's going to be a delta t here, and there's going to be a delta t here. So you're just solving it using Euler's method. So you would have x plus this term here, and then plus some noise. And this becomes a parameter which we need to fix in the calculations. And typically, the quantities or typical values for delta t are between 10 to the minus 3 to 10 to the minus 2. So how far your random walker jumps depends now on this time here. So the Langevin equation is a kind of more ad hoc equation, which was used to simulate the random or the Brownian motion of an object. The parameter d, when we look at the quantum mechanical definition of the kinetic energy, and we scale the equation by putting the mass equal to 1 and h bar equal to 1, then this parameter d just becomes equal to a half. So this will be a factor of a half, which comes from the kinetic energy operator. Now, when we go back to this Fokker-Planck equation, we can actually prove that there has to be a minimal condition on, or minimal shape on this probability f, this force f. So if we now look at the equations here, what you could say is that the resulting equation which we have when equilibrium has been reached, that means that your probability is no longer something which depends on time. So you would equate the right-hand side with 0. So remember now that when equilibrium has been reached, since we're dealing with a diffusion process, which is intimately linked with the Markov chain, when equilibrium has been reached, then there is no more time dependence. So that means that we have to set this equation equal to 0. Now, if we now spell out the equation, that means that 0 on the left-hand side can only be satisfied if all the terms of the sum are equal to 0, equal 0. So that means that when you take now the second derivative of this quantity, what you end up with is actually this quantity here. So what you have simply you take the derivatives, so you have the derivative of f and the derivative of p, and these are the equations which have to be fulfilled. And this is going to give us a kind of shape of the force F, which we are going to plug back into the diffusion equation or the Fokker-Planck equation. And then we can find an analytical expression for this transition probability. So it's a kind of messy approach here. So what you can show then is that this F, or this drift term, as we call it, has to be equal to a function g times the derivative of this probability with respect to x here. So this is the type of equation you have to fulfill. And the condition of stationary density means that the left-hand side equals 0. In other words, the terms containing first and second derivatives have to cancel each other. And that's only possible if this g is 1 over the probability. And it's actually pretty easy to see that if you insert it in the equations. And that is going to say that, or tell us, that this force F is something which now is defined by the gradient of the wave function divided by the wave function. And this is called a quantum force, because it's defined by a quantum mechanical wave function. So this term is the one which is responsible for pushing the walker towards regional configuration space where the trial function is large. That increases normally the efficiency of the simulations in contrast to just the plain Metropolis algorithm, where the walker has the same probability of moving in every direction. So what we are doing now is that we are simulating an object which moves according to the probability which we have defined. So we can solve this equation when we take the Fokker-Planck equation, and I'm not going to go through all the details. This is normally called a Green's function, if you're familiar with that. And this is the equation which we get. So we are going now to have a modified object. Instead of having f equal to 0, which we derived on the whiteboard, we are now going to get a quantity which will depend on this object f as a function of the position which we were in when we started. So taking x going to y is now going to give us something which will be proportional with f of y. So we, in the Metropolis Hastings ratio, the gx of y and gy to x are not going to even out in the sense that we just get 1 as a ratio between the two, but we will actually have something which depends on this specific quantum force, which is then given by the trial wave function which we have. So it means now that what we have to evaluate, and we're going to look at how we do that after the break. So we need a slightly more involved calculation, but this is going to replace the what we normally call the brute force or straightforward Metropolis algorithm with a jumping in space, which is conditioned by the trial wave function we've started with. So these are the equations which we're going to look at after the break. So I've taken the liberty of giving you the equations here. This will be the solution of the Fokker-Planck equation. It's a little bit more involved than the standard diffusion equation with no external force. You need to labor a little bit more to find this expression, but this is not so important for us. The important thing for us is actually the final expression, which we are going to implement in our codes. So I hope you can forgive me if I don't pester you with all these intermediate derivations. Okay, I propose we take a small break and come back after 15 minutes. So what I did now was to switch over to the Jupyter Notebook, which you also have access to. And when we now took the standard equation for diffusion and we added this quantum force, we can then find a transition probability. So this Green's function, which some of you may have met if you took a course in mathematical physics or mathematical methods, this now expresses a transition probability. So you can read this as the probability of going from x to y in a time step delta t. So we are going to sneak in an artificial time here for a random walker which jumps in space. And it jumps from a position x to a position y in a small time step delta t. So ideally, we would like this delta t to go to 0. But we will always have a finite discrete time step. And when we are setting up the code then, we need to actually plug in a value for this delta t. So what I wanted to do now is simply to guide you through some of the basic elements which you need to program. so that we take now this kind of top-down approach. And before the break, we actually concluded by looking at the requirements that the diffusion equation should have reached equilibrium. So you have the most likely state or the steady state. Then by simply looking at the mathematics, which has to be satisfied, we can say something about this probability. In our case, the probability is the wave function squared. That's the quantum mechanical definition. So we already have a model for the probability. And that leads to this object F, which is meant to, in classical diffusion, it's meant to represent some kind of drift force, which lets the particles or the objects drift in a specific direction. This now is, in our case, is going to be called the quantum force. So we have already calculated the gradient of this object when we needed the kinetic energy. So it means that we have expression for it. Alternatively, if we don't want to calculate it, we can use the automatic differentiation, which follows both Python in terms of autograd. Now it's JAX, J-A-C-X, which will be the software you need to install. And if you're programming in C++, you have a library called automatic differentiation, which you can download and link with your program. Sorry for that. So let me guide you through how we can now program this type of equation. And one thing you will notice in the program, if you look at the expression which you have now, which contains the ratio of the wave functions, and then the ratio between these two probabilities, is that one thing you would not like to do is to calculate the exponentials for both the numerator and the denominator. So what you do first is actually to take the ratio between these two quantities and then calculate the exponential. Because calculating two exponential is something which becomes extremely time consuming. So any of these operations which we can save are very important. Another thing which I wanted to mention to you before we start looking at the code is actually how do we calculate the ratios between wave functions. So let's take a look at the whiteboard here, because this is an important technicality which we need to pay a little bit attention to when we now are thinking of designing the program. So let's go quickly back to the whiteboard. And this is an important technicality which we need to pay attention to. So what we have is this ratio, which we call for Q in the slides, Q of Y of X. And this is going to be given by the wave function squared, or a trial wave function, as a function of Y. And it's divided by psi of t and of x squared. And then we had this Green's function, which now contains y, x, and it contains this time, delta t, divided by this g of x of y of delta t here. Now, if we look at the wave function, there's an important aspect. So for systems which are weakly interacting, there are some simplifications which lead to considerations which we have to think of when we are setting up the Metropolis sampling. For systems where the single particle picture is a meaningful starting point, which essentially means systems with weak interactions, which you would find in systems like these bosons, which we're looking at in project number 1, or systems like atoms and molecules, or in many solid state systems, then what's normally called a mean field picture or an independent particle model is a useful starting point. An independent particle model is a useful starting point. So what does that mean? That means that the trial wave function, as you've been looking for, as you've been studying now with the harmonic oscillator only, so for no interactions, this is the idealized case, we can actually set up the trial wave function Ct of r is actually given by the exact function if this is a product of single particle wave functions. So this is going to be a product, write I equal 1 up to n. So just think of the plane harmonic oscillator. So this is going to be a psi of I, and this is now going to be a function which depends on the single particle degrees of freedom. So that is going to be an R of I. So the wave function is now given by the product, or we should rather say proportional to the product, because we have to specify whether this is an antisymmetric or symmetric trial wave function. But let's just write it proportional. So the exact one here would have to be symmetric or antisymmetric, if we are dealing with fermions, for instance. But what we can have now is a system which we can solve exactly. So this phi of I, we would have a single particle Hamiltonian, H, and I write this in terms of an operator. So that is going to be given by H squared divided by 2m. It's going to have a derivative, the Laplacian, which represents the kinetic energy. And then there's going to be some external potential, which in our case is the harmonic oscillator potential. And I'm just going to write it like this, Ri. And then I'm going to put and label external here, just to indicate that the particles are now moving in an external potential, which is being set up in one way or the other one. So the harmonic oscillator is actually something which mimics realistic systems. So a system which led to the Nobel Prize in Physics in '89 was the physics of Paul and Penning traps. So after the two inventors of these traps. And you can then set up electric quadrupole fields, and these are used actually in this system of bosons. And electric quadrupole fields go like x squared plus y squared plus c squared. So they are harmonic oscillator lookalikes, but they are harmonic oscillators with a finite depth. So that means that you cannot sustain an infinity of single particle states. So this means that when you look at this H of I, so that is the system H of I here, so that acts on particle I. And now I'm just going to change a slightly notation here. So this is going to be an eigenstate, lambda. This is going to be given by some lambda of phi, lambda of R of I. So if we have that, then we know that the trial wave function is just the product of single particle wave functions. So this means now that when we look at the ratio here, psi of t in a position which we call for y, so for the many particles, so let's call this y. This is a new position. And then we have to square it and divide by the previous position. So this will be the position we call x for all the particles. So what we have then would now be the product of all these single particle states. So that means that we would have, and now I'm just going to write it out. So we would have psi of 1. So there would be an R1 of y. So this is squared. And this is all the way up to psi of n of r n of y. And then divided by psi 1. And this is in the previous position, x. So this is squared. And then we have the product up to psi of n squared of r n of x. Now, if you look at this ratio here, so we could now choose whether we want to move all particles and perform the Metropolis tests, So we have two choices here. So one, move all particles. So all particles are in the position R of X, and then we change the position of all the particles and perform the Metropolis test. So we suggest a move where all the particles are moved, and then we perform a Metropolis test. Or we could actually just move one particle at a time, and each time we move it, we could perform the Metropolis test. So the way we perform the Metropolis test is something which we can decide upon. So move one particle at a time. And perform the Metropolis test. So what I want you now to look at is the type of trial wave function which we have. If you add correlations there, it's going just to complicate it only slightly. But so what you could say now is that the general picture is the one which you see in this equation above here, where you have to evaluate the ratio. So if you look at this now, which strategy would you think, or do you think is the most efficient one? So feel free to unmute yourself or answer in the chat. So I'm just going to give a number to this, 1 and 2. So we could have a vote now, right? So who votes for 1 and who votes for number 2? Maybe we should have had a poll here. So which one do you think is the one which is most efficient from the point of view of saving CPU cycles? So we have a several one. So it seems that, guys, you seem to be equally distributed among 1 and 2 here. Actually, the one which is most convenient is to move one particle at a time. This will become very apparent or clear when you also are dealing with fermions and setting up a Slater determinant or determinant. So actually, choice 2 is the one which is the one which saves you more CPU cycles. And the reason for that is that your wave function now, if you move all the particles, you actually have to calculate the new wave functions for all the particles. So just if you look at a little bit more closely at this ratio here, so if you move one at a time, what happens then? So in that specific case, take this one. So suppose we move particle 1, first particle. What happens then is that the only thing which changes, so you have 1, and then we would have an R1 in a new position, and then we would have a Y, sorry, phi. So this is squared, and then we would have phi 1 squared in the old position, but all the other ones are the same, so they cancel out. So in the calculation of the ratio here, I only need to look at one function at a time, whereas in the other case, I have to move all the particles, and I have to, when I calculate the ratio of the wave function, I actually need to calculate all the small changes. So when I do one at a time, what happens then is that my ratio simplifies, because the other ones are just staying in the same position. So in the other, I would have a psi 2, and this would be an R2. So let's put vector on it in a position Y squared. And this is the same as before. So this is actually the position which we had. So this will simply be 2 in x. I would have a psi 2 of R2 in x. Nothing has changed here. And then I would end up with a final one, which would be an Rn of x squared divided by a phi n of an Rn of x. So all these terms here would just simply cancel, and I'm only left with a much simpler ratio to evaluate. So when you then start calculating the number of cycles, what you will see is that this simplifies the calculations. And it means that we only need to look at the change for each individual particle at a time when we have a physical system where the interaction is weak and where it makes sense to have a wave function which contains a single particle part multiplied with an interacting part, where you have at most two particles interacting at a time. So in the slides, we are going to go through some of these kind of technicalities now. So they're not so exciting, but we have to think of them. The example which you will find in the lecture slides is a case where we now have a system of two electrons which interact via a Coulomb interaction. So it's slightly different from the system we have. If you take away the Coulomb interaction, it's just going to be harmonic oscillator. And in that case, the wave function will just be the product of these single particle wave functions. So these are some considerations to think of when you're setting up a code. And here, the physics of the system is so that it actually favors an approach where you flip just one particle at a time. Because then the evaluation of the ratio in the Metropolis algorithm is the one which is favored by just moving one at a time. So this depends, as I said, by the physics of the system. If you have a system which is strongly interacting, this doesn't make sense. And then we would have to move essentially all particles and then perform the Metropolis test. But if we can move one at a time and simplify the Metropolis test calculation, that's something which will speed up the program considerably. So you're going to waste a lot of cycles in the Metropolis testing, because we are doing this millions or billions of times. So if you can speed that process up, that's gold. So let's go back to the Jupyter notebook then. And I'm going to show you this example and how we can implement it. The other thing to think of is how we speed up the calculation of this so-called ratio between the transition probabilities. So one is to speed up the ratios between the wave function squared, and the other one is also to speed up this quantity here. So as I said, this ratio here, which you're going to compare with a random number, is something you will compute billions of times. And this is one of the places, in addition to the local energy, where you're going to spend a lot of CPU cycles on doing. So anything which can make this calculation efficient is, because this is one of the bottlenecks of your code, anything which makes that efficient is something which we need to think of. Now, the beginning of the code is just me preparing for writing out the data to file. So the first thing which I have now is the trial wave function, which now contains a correlated part. So if you go back to the exercise we had the first week, where you were supposed to write or write out the analytical expression for the local energy, this is a case where I now have two variational parameters. I have a variational parameter alpha on the single particle piece. So my wave function is the product of two harmonic oscillator functions, which you can see here in 2 dimensions. So this is a 2 electron in 2 dimensions, and they interact with a Coulomb interaction. So this means that my wave function is a single particle harmonic oscillator. So this is the argument. X squared is the first one, Y squared is the second one for particle 1, X squared for particle 2, and y squared for particle 2. Then I calculate the relative distance between particle 1 and 2. So this is the x component squared, and this is the relative y component squared. I calculate my denominator, which I need in the exponential. So you can see here, this is also something which I do in order to speed up the calculation. So I do not calculate the exponential of this quantity and the exponential of these quantities, but I do the exponential of the final argument. That saves CPU cycles as well. So every call to an exponential, even if this is a highly vectorized function, is something which steals CPU cycles. So then I have the local energy. And in this particular case, what I've done is actually to set up the analytical expression for the local energy. So I could have computed the kinetic energy numerically, but now I'm simply setting up my local energy. And you will see that my local energy has also, so this denominator which you see in here is, or this R12 here, is something which now gives you the Coulomb interaction between, this is a repulsion between two electrons, which is 1 divided by the relative distance, the absolute value of the relative distance. That's why you have the square root of here. And then I have additional terms which follow from the second derivative of the trial wave function. The next thing which I need to set up is this quantum force. So what I'm setting up here is the gradient of the trial wave function divided by the trial wave function. So this is now my so-called quantum force. And in my case, I have now two variational parameters here. So this is just an example on how you can set up the code. And you need to think of how to encode this part in order to implement importance sampling in your code. Then we have the Monte Carlo sampling. And here I'm setting up this importance sampling. So I have my position old, my position new. I calculate my old quantum force and my new quantum force, because they are needed in the setup of these ratios of probabilities. So I know that my minimum is at alpha equal to 1. I have a harmonic oscillator, has the way I've set up the harmonic oscillator wave function is by having a minimum with the non-interacting case where alpha is equal to 1. The interaction is very weak, so I shouldn't move that much away from a minimum for the parameter alpha, which is equal to 1. Then what I'm doing now, I'm setting up the positions for all the particles. I set up my old wave function and my new and my old wave function. So this is just me initializing the wave functions and the quantum force in terms of the parameters alpha and beta and the old position. So my old position now is given by a normal distribution. And this is my normal distribution now, scaled with this time step, which is a parameter. And it's a normal distribution with 1 as a variance and 0 as the mean value. This is a pretty standard choice. And then I'm now setting up the new position, and I use this Langevin equation. So it's the position old, and then it takes the square root of this time step and the normal distribution, and it has a quantum force times this time step times this d, which is equal to 1/2 when I have used units, so that h bar is equal to the speed of light, is equal to the mass of the particle, is equal to the electric charge, all the constants which we have set equal to 1. And this is normally called atomic units. Then I calculate my new wave function. And you see now that I'm running, if you look at the outer loop here, I'm running over the number of particles. So then I calculate this Green's function. I look at the dimensionalities. And now I'm taking the arguments for the Green's function, or this probability, transition probability, in the numerator and the denominator. And I'm setting up the quantum force in the new position and the quantum force in the old positions. So this is just the ratios which I'm setting up here. And then when I've done the ratio, the arguments to the ratio, then I calculate the exponential. So I wouldn't calculate the exponential of the numerator and the exponential of the denominator, but I actually set up the argument and then do the exponential. And here I've actually done, I haven't been as efficient as I promised, because here when I look at the new wave function and the old wave function, I could actually have simplified that. Because if you now look at what I'm doing, so I'm moving one particle at a time. It means basically that the position u now is given by the simply the move of the next particle. But the what I could do is actually to change that so that I could simply implement a wave function now, which simply depends on the position of the particle which I moved. So in here, I haven't been fully consistent with what I preached on the whiteboard, because I could actually have simplified this ratio of the wave functions. So keep that in mind in this code here. Since I'm only running for 2 particles, I'm a little bit lazy. So I didn't, how to say, fine-tune this to a multi-particle case where I just move 1 particle at a time. So keep that in mind when you watch this, this test function here, or this example. This is very much specialized to the 2-particle case. And for 2 particles only, you can be a little bit sloppy with the attention to how many CPU cycles you want to spend. So then, when I've calculated the ratios, then I calculate a random number according to the uniform distribution, and I calculate that one to the, relate that one to the ratio probability. And if this is less or equal to that one, then I simply update my old position with a new one, and I update the old quantum force with a new one. And my old wave function is equal to the new one. Then I calculate the local energy, and then I update the parameters, and then I perform the final calculation of the energy and the energy squared, and then I can do variances and so on. And here you can see the definition of the system. I have 10 variables, 2 particles in 2 dimensions, and then the rest is just a plot here. And when I've done importance sampling, you will also find an acceptance ratio, which is close to 95% in general. And here, this is a little bit rugged, the surface, because I didn't take so many Monte Carlo cycles. So in this specific case, I run with 100,000. So I should actually have run, to get a smoother curve, I would have actually have to run with close to 1 million. But you will see that the minimum is around 3, which is the exact value in 2 dimensions. And it has a parameter alpha, which is around 1, slightly above. And then it has a parameter beta, which is around 0.28 to 0.3. So this is roughly where you would have the minimum here. And it's pretty close to the exact wave function, or the exact result here. Okay, any questions so far? So this is just a kind of a demonstration on what you need to program. And hopefully you can see the basic ideas from that before you start implementing it, before you start implementing importance sampling in your own code. So what I'm going to do now is to go back to the slides. And now comes the slightly more boring part, because now we need to look at some technicalities here. So these are examples of codes. And what I've done here is actually to bring up a collection of expressions which you need to think of. So when you're setting up the correlated part of the wave function, this is where we need to think a little bit. So what comes here is not that exciting, but it's important for what is coming. So till now, we have put an emphasis on the non-interacting case. That means that your wave function is, your trial wave function is essentially going to be a product of single particle wave functions. So what we need to think of now is how we move from that to the case with a correlated part. So C here stands for your wave function. If we just go back a little bit to to the whiteboard before we move on. So let me just remind you of that. So when we are setting up the total wave function of a psi trial as a function of the different particles and the variational parameters alpha, that is going to be something which is given by a product of single particle wave functions, I equal 1 up to n, and then we have a phi I, and then we have a function of Ri like this. So this is what we are doing now. And I would suggest that when you're now developing the code, when you do the benchmarking and testing of all the different elements, we stay with a non-interacting case. But this is going to contain also something which we are going to call a psi of C. So this will also be a function of the variational parameter. And this psi of C is something which is normally called the correlated part of the wave function. So correlations, correlated part, or often called Jastrow factor. And this is meant to mimic the type of correlations which come due to the interactions. So this contains the physics of the interaction. And that interaction, which we write as a V as an operator, is just the sum over all the particles which we have as an I less than j of n. And then there is an interaction here which typically depends on the relative distance between the particles. So this Rij is actually given by x or R1, Ri minus Rj. So that's the relative distance. So most interactions which we are going to deal with are interactions which depend on the relative distance between the objects. So our interaction is now going to be the total one, is going to be the sum over all the interactions between two and two particles. And I would normally put it like this because this the hat is meant to represent an operator. And typically the type of potentials which we end up with, so this V little hat Rij is normally proportional to some kind of constant gamma divided by the absolute value of the relative distance. That's one of the most common potentials. And if you look at the Coulomb interactions between two particles, or if you think of the gravitational force, many of the fundamental forces in nature, they have this kind of dependence. That means inversely dependent on the relative distance, the absolute value of the relative distance. So when we now go back, that means that what we are going to have is a trial wave function, psi of C, the correlated part for the trial wave function, which is often given by some kind of function which is defined by some minimal constraints which the wave function has to have. And a typical form of this wave function is given by an exponential. And you can actually show that mathematically that is a minimal requirement which is needed to cancel some specific divergences. So when I write this I less than j, it's actually a double product. And the same with the sum here, it's a double sum. And that runs over all this f of Rij. So f of Rij is a function which depends on the system we are studying. So this is system dependent. Now, in our case, you've gotten a specific form for that. And we are now going to go a little bit back to the slides again. So let's do that. So as you can see now, one of the things we need to think of when we are calculating derivatives, so when we calculate the quantum force, we would need something like this. So this is a derivative with respect to a particle k. And we need to plug in a form like this one. So there are some mathematical exercises which we need to go through. So typically when we calculate the different quantities, we can make simplifications depending on the type of wave functions which we have. So we would, when we set up the ratio, we have the wave function squared divided by the new one divided by the old one. But what we need is actually to set up something which depends on the new wave function divided by the old. And then we would have a one body part, which is what you have been studying now, just a plain harmonic oscillator product. And then you need a part which depends on the correlations. So OB stands for the one body part. So it could be a Slater determinant or product of boson single particle states. While this psi of C is our correlated function, or just the Jastrow factor. So we need to find this one. So that's an important place where we're going to waste a lot of CPU cycles. We also need to optimize the calculation of the ratio between the gradient and the wave function, because we need that in a quantum force, but we need that one also in the calculation of the kinetic energy. So when you calculate the quantum force, there are things which could be reused, or the expressions at least, when you calculate the second derivative. So we have this ratio, which is now, when we just set up the equations here, we need now the ratio between the one body part and the derivative and the correlated part. And here, the reason why I'm focusing on this, and it may not sound that exciting, but this is the part where we need to use the insights about the wave functions in order to find an optimized algorithm which saves CPU cycles for us. So we would have now a derivative here. And if you move now one particle at a time, this derivative will only act on one particle. So that means that the ratio here would simplify to the calculation of just the derivative of one function at a time. We can also simplify the calculation of the ratio between the derivative of the correlated part, the gradient of the correlated part, divided by the correlated wave function. So keep this in mind. I mean, the expressions here are pretty simple, but the way we simplify the code and optimize the code will depend on the type of trial wave function which we have. And then we have the other quantity where we need to pay attention. So we need the expectation value of the kinetic energy. And in this case, the I here stands for one particle. It could be an electron, it could be a boson. And we need to optimize this ratio as well. So when we calculate the local energy, that will contain the sum of the kinetic energy for all the particles. So if you move one particle at a time, then you need only to update it for one particle. And there are simplifications which can be made depending on the analytical form of your trial wave function. So when you look at the second derivative, again, you need some additional terms. So you will have the second derivative of the wave function for the one body part, plus the second derivative for this correlated part. And then you will have the dot product between two gradients. So keep in mind, these were actually the kind of equations which you were asked to study at the first lab session, where we did the paper and pencil exercise. So these equations here are very important to look at again, in particular since we are thinking about how we can optimize the calculations. So what comes now is actually a series of simply manipulations and how you can optimize these things when you write your code. So I invite you to take a look at these derivations and try to think of these kind of details when you now are writing your own code here. So the thing which is easy to calculate is the one body part. That simplifies immediately because when you take the derivative with respect to one particle at a time, all the other particles, they in the denominator and the numerator, they cancel out. And you're only left with studying the derivative for one single particle at a time. So that this piece here is normally the easy part. The nasty part comes when you're dealing with the correlations. And the slides here, the end of the slides here, they actually contain the kind of expressions you could consider when you're setting up the derivatives. So most of the interactions, they depend on the relative distance between the particles. So this is a function which you can rewrite in a more compact way like this. So this product here is a double product of I and j. We don't have self-interactions. That's why this sum goes from I plus 1. So the particle do not interact with itself by obvious reasons. And the manipulations you need to do now when you plug in this specific ansatz, this is a very common ansatz for the trial wave function, because this is an ansatz where you can cancel a divergency when two particles are getting close to each other in the kinetic energy from 2 and 3 dimensions and on, and from the potential energy. So this is a kind of minimal requirement on the wave function, which can cancel divergencies in the kinetic energy and in the potential energy. So what comes here, and I actually invite you to take a look at these expressions. This is not the most exciting thing we can present during a lecture. So the lecture serves more to guide your reading. So what follows in the slides from here and on, from slide 22 and on to roughly slide 27 and 28 and 29, is actually a review of the kind of elements which you need to think of when you're setting up your code. And one of the things you need to is also to check that when you calculate it like the local energy, you have a derivative with respect to a given particle, which can be simplified in terms of the function f, which is the function which now defines your specific wave function. And you need also the expressions for the quantum force, which can also be simplified when you're setting it up here. So in the slides here, there's also a hint on the kind of random number generators you can use if you're writing everything in C++. And we normally recommend this Mersenne twistor class of random number generators, which is then given in terms of this MT 19,937. This is the 64-bit variant. And this is a random number generator which produces 2 to the power of 19,937 different random numbers. So it's a huge number. So even if you run billions of Monte Carlo cycles, you will always produce different random numbers. And this is a random number generator which has been tested again and again. And it's called the Mersenne twistor class of random number generators. And we normally recommend using that one when you write your codes in C++. There are also examples on how you can implement this Green's function in C++. The thing which we have not covered, which we will discuss a little bit next week, is about the derivations of the Fokker-Planck and the Langevin equation. So what I wanted to do now was more to give you the kind of overarching view of what we need to program. I invite you to take a look at this Fokker-Planck and Langevin material. We will discuss a little bit of that next week, but next week we will also start looking at other things which are important to program, and that is something which deals with gradient optimization and resampling techniques. So I'm going to stop the recording here now.